Swayam Prabha. Digital India. Educated India.
We are going to go a little bit more in details about this compliance. Okay, so we have already seen its utility in the CD-ROM drive case. Okay, you remember that we had had this block diagram of the block which is supported by these wires, and that was like hanging in the magnetic field, and it has some kind of a coils. When the current passes, then that block moves and it controls the length of the CD-ROM drive. Okay, that system we have already seen, and that system is used in CD-ROM drive for the fine positioning, as you remember, fine positioning or fine tracking, and then fine focus kind of a control. Okay, so so now let's see, like, formally, a little bit more formal kind of a, like, why compliance people want to use in the systems. As you can guess, like, it will give you high precision positioning with a moderate range, so not very large range that can be possible. Then it can have high speed possibility, because when you use compliant elements, typically the weight will go down. So when the weight goes down, you can kind of, like, have higher speeds possible. But there is a flip side to it, that because of the compliance, you'll introduce some kind of a vibrations in the system, and one has to do a good control strategy to kill those vibrations off. There is no backlash, no wear and friction in the system. Okay, so this no wear in the system is because, like, there is no two elements rubbing against each other, so you don't need any lubrication, maintenance, nothing, that will be gone. Then there is very, like, low energy requirement because the mass is less. Then you have higher durability because there is no friction, there is no rubbing of the elements, and see, this rubbing of the elements over the long duration of operations would really cause some kind of wear and tear of the system, and that's where, like, one needs maintenance, and then the durability goes down and things like that. They are absolutely noise free, again, because there is no rubbing of things against each other. See, you might have heard some motors, when they move, like, they make some kind of a noise, mainly coming because of the bearing and, like, imbalance in the system, which will create some kind of a noise. So since there is no friction here, again, no noise, no lubrication. Okay, so these are a lot of these different interesting advantages, and that can help really in very high precision positioning, which is required for this era. I mean, when we are talking about a nanotechnology, microtechnology, already coming up in the market in big way in many different devices, like, obviously, like, high positioning, high precision positioning systems would have a, like, better prospects to go. And compliant, compliant mechanisms is one of the promising candidates towards that, and people have started using compliant mechanisms based positioning systems, nano positioning systems. There are some kind of a basic motion elements that could be identified here, where, like, you can have a rotation possibility. So you move this, like, some kind of a construction which will make the stage rotate without really having a rotary kind of a hinge joint in the system. Okay, or you can have a translation possibility, or you can have a screw kind of a possibility. Okay, so these are kind of, like, some basic kind of motion elements. What we have seen in CD-ROM drive is this kind of a translation element, which was used. So you instead of, like, these kind of a plates, you can think there are these kind of a 3 wires here, 1, 2, and 3 here, and 3 wires on the other side. That will give you the same kind of a motion in the direction that is shown here. In addition, like, because these are wires. See, for example, this stage doesn't have a motion possibility in the perpendicular direction here, as shown by the laser arrow. because because the stiffness of these plates in this direction bending is way too high, so they can, it's like a scale which you can, or a flexible link. Okay, I can show you here the link which you can bend very easily, but you cannot, if you want to bend in this plane, it is not possible to bend it. Okay, it's very difficult to bend in this kind of a plane. Okay, so this is basic elements of motion for compliant mechanisms. Now I'll just give you this linear kind of a motion stages in compliant mechanisms. So this concept here is very simple. If you say, okay, I want this block to move in the linear fashion, and it should be guided only by the compliant kind of a mechanism. So if I attach one kind of a cantilever beam here, then the motion of this block, as you see here, or this cantilever system is deforming like this. Okay, so it has some kind of a deformation. Okay, so this block is this block that is not really moving in a straight line fashion here. It's moving in some kind of a so to say, like some circular arc kind of a fashion. Okay, so this block also is undergoing some kind of a if you see this little bigger size here, yeah, this block also is undergoing some kind of a rotation. Okay, so it was like this here, and then in this it is tilted. Okay, so this rotation is something which is not desired. We want this block to move exactly like a straight line down below. Okay, so for this now we introduce some two elements of the same kind. You just don't have one single beam, but you have two elements. Okay, I'll show you in the block here. Okay, so you have this now. So you have these two elements here. Okay, so this was a single element. Okay, bending, and now you have these two elements. Okay, so you can see that this bend, it is moving parallel to itself. Maybe I can change the okay, you can see that this moves in a way that the block is moving parallel to itself. But if you see on the carefully here on the slides here, you see that there is still a parasitic deformation in the other direction. So there is some axial motion that is happening here. Okay, this unwanted deformations are called parasitic errors here. Okay, so to prevent that, you introduce one more such a system. Okay, like this. Okay, so you have introduced now two additional beams here, and this stage is additional stage here. This is a moving platform. Okay, remember here it was a fixed kind of a wall, but now this is a moving platform here, and the fixed ends are up here. Okay, these are the ends which are fixed to the wall somewhere here. Now if you imagine this if this would have been fixed, exactly the motion that you have seen earlier, like this, that motion happens, would have happened. Okay, so and then now if you just imagine that this block is not there and only this block is there, then if I give a force which is same force that I was there here, then I will get deformation in the same way as was happening for this block, but in the opposite direction. Okay, the parasitic error that is produced will be in the opposite direction. The deformation is in the same direction, in the same downward direction, but the parasitic error that will be produced, the parasitic error in this case is going to be in this direction. But when you move this block down only without having this block, then the parasitic error produced will be in the opposite direction. Now when I see this in combination, that okay, this block is applied a force, the reaction force is transmitted here, which will deform these two outer beams. Okay, so that gives this deformation in such a way that this block is actually now having some kind of a parasitic error of motion, which is compensating the parasitic error of this block, and that's why this block will move completely in the straight line. Okay, that you can see up here. Okay, so this is a mechanism where you can see that let me get it here clearly. So See this, you can see there's a 4 beams here, 1, 2, 3 and 4, and then like you see this block is moving in the exactly straight line. Okay, actually you can put a pen here and see, draw it on the paper, and you'll see that this motion is completely in a straight line fashion. Okay, because this block is absorbing that parasitic error. Okay, so like that you can have a compliant mechanism design, and as you can see naturally, like this keeps on vibrating. Okay, keeps on vibrating a lot. Like if I give this deformation, this keeps on vibrating, and like for long duration. And this block is made up of material called beryllium copper, which is having a high fatigue strength material. Okay, so this is how like one can get perfect straight line motion here, and this can be utilized in our lot of mechatronic systems for getting like a straight line motion which is at the nanometric kind of accuracy. Okay, and like now a bigger kind of a little bit bigger scale than our CD-ROM drives. Okay, so CD-ROM drive has this principle only up to this point. Okay, so CD-ROM drive didn't have this parasitic error compensation. Okay, so there will be parasitic error in the CD-ROM drive case a little bit, but it's okay that it will not bother. If you see carefully, this kind of error will not bother any functioning of the CD-ROM drive application. Okay, so this is the main kind of a concept for like having a linear motion with compliant mechanism, and there can be a lot of these possibilities. Like many different kind of a compliant mechanism possibilities could be there. And nowadays, because we can 3D print devices, we can print these mechanisms very easily in polymer material, for example. Metal is still difficult, but like with EDM and other kind of processes, we can cut them in the metal. But with the 3D printing, very interesting kind of mechanisms can be like readily printed in plastic kind of a material, if that is okay for whatever application you are trying to drive. Okay, so you can see some more links of compliant mechanisms here, and get yourself a little bit more familiar with them, so that you can think whether you want to use them like in your project or in any other application in the future you might be considering. Okay, so we have this concept seen for CD-ROM drive. Okay, that is again like I'm showing the picture here. So this same concept as we had for this block up to this point. Okay, that is acting here. Okay, when this force is given, like you had seen like when we deform these, like these beams undergo some kind of a deformation. Okay, so just to recall you, this same case is there in the CD-ROM drive. Okay. Now there are many different kind of other possibilities. So you can have a two-stage compliant mechanism. So this two-stage double parallelogram kind of a mechanism, or like you can have rotary joint with compliant mechanism. So two-stage means like you have X stage motion possible and you have Y stage in the same way. Okay, you think about how this can be possible for having X stage motion and Y stage motion in the similar kind of a the compliant elements are put in such a way that you have X stage motion also possible, and for the same stage the Y motion also is possible. See, one of the very easy ways is to kind of like say that okay, my X stage is carrying my Y stage and they are kind of like in the series. Okay, and they are like the whatever motion that happens for the X stage, the Y stage motion will be like Y kind of a mechanism is put in such a way that the motion produced by that Y will be perpendicular to what the motion is produced by the X, and the Y stage is actually hosting or carrying the X mechanism. Okay, that is very easy to see. But like if you want to kind of have the same stage, but it will have a X and Y motions possible in the same way as what we have for the single stage, then like it's an interesting case to think about. So think about that, and like we'll see if at all time we can discuss this a little more. Then you can have a rotary joint with compliant mechanisms. This is little I've shown you one kind of a case. There are many different other kind of cases that can be possible. One simple case is like your cantilever. Okay, so if you see this cantilever, this motion that is happening, like one can kind of fit a circle to this motion and say that okay, center of that circle will be like my virtual hinge point. Okay, and that appears to be like that. Okay, so it moves in a fashion that okay, it almost traces there's like some small little circle here. Okay, then you can have this bistable mechanism. This is very interesting kind of a case. You might have seen this kind of a mechanisms. Let me see. Yeah. So they are like now having two stable states. Okay, so let me again show this here. Okay, so can you all see these? Maybe I need to move from my side. Yeah. So you can see that there is a beam which is here. If I push it, like it goes and like makes this click sound and goes down. Okay, maybe I can bring it more closer here so I can show you this beam. Okay, you can see this beam. Okay, so if I push it, it is now like bent like that. I push it like from this side, it goes on the other side and makes this click. So it is moving these two stable positions. Okay, so maybe yeah, maybe I will show you it in this angle. So you push it, it goes like that. Push it like that, it goes down. Okay, and these are like one position is circle down and one position is circle up, like that. Okay, so these are the positions in which it will go. Okay, so a little more closer. Yeah, you can see that. These are the bistable kind of a mechanism system. They are stable two positions, but middle position is not stable, and they are very good for switches. Okay, so switching application, you are actually some of our like home switches does have this, but they don't have the beams there, but they are spring based kind of a compliant mechanism systems are there. They are springs based, but not like really this beam based. Okay, so the spring actually kind of gets two positions, so that's why like use your switch at home that has these two toggle positions, like you switch off and it toggles and sits in that position, and like you switch on and it toggles and switches into. So that is again like that is a bistable kind of compliant mechanism. So they find like a lot of usages in our day-to-day system as well. Okay, so we'll see a little bit on the analysis of a simple analysis for getting these approximate solutions for these compliant mechanisms for the small deformation. Why approximate solution? Because they are for the small deformation kind of cases. So I'll tell about like a little bit broader scope of this analysis and study, and then like we can focus on like just getting simple solution like by using whatever theory we know a little bit about Euler-Bernoulli beam theory. We may apply it and like see some simple cases. Okay, and for more detailed analysis you have this CBCM, that constraint beam this beam constraint model method, okay, or chain beam constraint model. Okay, so this is a very recent kind of a development in the literature, which we may not get into the details, but like you need to kind of say that okay, there are like FE analysis techniques, and there are some other kind of a simpler like this is a computation little more efficient than FE analysis. That's why this is a good method in the literature, very recently proposed. So just to kind of sensitize you that okay, there are a lot of these different analysis tools that are available out there. One can use it if you want to kind of like do the analysis more, the simple analysis to get, and then we can have a more detailed analysis. Then there is for say buckling is still like an issue, like there is not a lot of literature of buckled beams and post buckled kind of a beam analysis and things like that. So accounting for buckling is a little tricky issue in this, and there is some literature and there is some more literature that is to be explored. I mean, it is coming, some papers are coming in this area, post buckled beam vibrations and things like that. Okay, especially large deformation is problems are not yet solved. Okay, so this analysis has a lot of like rich possibility of different problems to be looked at and solved. And kind of analysis typically will be structure that will be used in this analysis will be like cantilever structures, or like with different kind of boundary conditions. You can have multi-layer structures and things like that. Okay, you can have flexure hinges, okay, which are rotary kind of flexure joints. So one can have some kind of a approximation done in modeling, saying that okay, oh, instead of cantilever, I'll model this as some kind of a torsion spring there, which is having like center, some known center, and then kind of go ahead with the modeling and things like that. So there are a lot of these models people have proposed in literature, and they are available. Okay, so this is kind of a table which captures somewhat like what kind of analysis and theory that is required to be used for say static and dynamic analysis for different kind of cases that you have. So, so for example, cantilever beams, single or multi-layered, those kind of simple structures, you'll do static analysis, some beam bending theory, mostly Euler-Bernoulli beam bending theory with a small deformation analysis. Then you may have thermal analysis also possibility for the cases where like you have expansion in the structure to be considered in addition. So the thermomechanical kind of analysis one can do. Okay, buckling theory we can use for compression kind of analysis. Okay, and for dynamics, like again you can use Euler-Bernoulli beam with a simple something called assumed modes method. Okay, so we may not be having time to go through this kind of technique, but this technique is good for many control kind of applications. Of course, you can do FE analysis for dynamic analysis study, but FE modeling is not amenable many times for a good controllers to be developed based on the FE analysis alone, because that model becomes really many degrees of freedom kind of a model, where assumed modes method can be having only 2 or 3 degrees of freedom kind of a model can be produced with the assumed modes method. Okay, which will suffice for like lot of like small deformation kind of analysis of beams. Then in the torsion, you can have torsion theory, static rotation of micromirrors, and so these are some of the applications given here. Okay, comb actuators or biosensors, then all these compliant mechanisms we talked about. Till the time we have like small deformation analysis. Okay, then micromirrors with these attached to. So AFM cantilever is there like in AFM mechanism. Okay, so those kind of things can be analyzed nicely with you using simple Euler-Bernoulli beam theory. And then you can have plates or rectangular or two-dimensional kind of compliant elements, and they can have different ways of like typically FE way will be there for the finite element method will be used for static and dynamic analysis here. Okay, so this is a kind of a way typically like the structures will be analyzed. Okay, we'll not get into all these details. Like if you are interested in some more components of these, we can go through. But we'll some small analysis will focus on Euler-Bernoulli beam analysis to kind of get some kind of a flavor of some of the compliant mechanisms, how one can apply such whatever the things that you have done in Euler-Bernoulli beam theory. Okay, so so this is what we will do analysis for by using Euler-Bernoulli beam. So all like this formula. I'm presuming that this comes from Euler-Bernoulli analysis of planar section remain plane, small deformations, or like the deformations are relatively small as compared to the length of the beam. There are no shear effects. Okay, in the lengthwise direction. Of course, there is a shear in the cross section, shear force is there, but in the lengthwise direction there are no shear effects. So these are kind of very what you say, lot of assumptions which are maybe working for small deformations only. They are not really large deformations. These kind of assumptions will not work. But people do that to kind of get some kind of theoretical base to kind of analyze at least small deformation cases very well, and for large deformations one can build on this theory further to incorporate large deformation analysis and things like that. Okay, so let's kind of like apply some of these Bernoulli beam techniques here. So you are given this length to be say 500 mm and then thickness to be 2 mm, and this is a machined out of 35 mm thick slab by using EDM process is what is given. That means like this you start off with the 35 mm thick block, and like you start cutting this block like along these lines to get this material from here removed, so that you get finally this mechanism. Okay, so this material from here, here and here is removed in some way, and like you get finally this mechanism to be in place. And so the width of this beams here is going to be 35 mm. Okay, and the aim is to determine say some actuation force needed to move this mass by 5 mm and things like that. Okay, so you can think about here, pause here and think about, okay, how will you apply that Bernoulli formula here to kind of see how do you get this deformation. Okay, so one can think of what are the boundary conditions for the formula to apply, and what is the moment that will be coming on the system. Okay, either you can work with the moment or you can work with the shear force. Either way is going to be giving you the same thing. Only thing in you need to make sure that you consider the boundary conditions really well. So I would say you can think about this analysis and do some stuff. I mean, I think there is a good. It will be good if this is done, and then we discuss it more. Then whatever doubts you have can be clarified much better. Okay, so I have given some kind of a guidelines here to see, and you don't look at these slides unless you have done something on your own, okay, and got stuck somewhere, or you have got solution also, then no problem. Then you can have a look at and check whether your solution and these matches or what you have missed. So this is what is the exercise that you would do.